All right, can you see the slide phone?
Yes, yes.
Okay, now let me remind you the row theorem and mean value theorem. So it's very easy to memorize row theorem and mean value theorem. They have the same assumption. Here, Fe continuous on the closed interval AB and differentiable on the open interval AB. Differentiable on the open interval AB is mean f prime of x at this for any x of the open interval AB. Okay? And if Fa is equal Fb, then there exists a number C between A and B, so thus f prime of C equals 0. It means that there exists a number C between A and B, so thus the tangent line to the graph of the function f at the point C at C is parallel to the x-axis. You see? And if we don't have the condition Fa equal Fb, just Fe continuous on the closed interval AB, differentiable on the open interval AB, then there is a number C between A and B. So thus f prime of C equal Fb minus Fa over B minus A. F prime of C give us the slope of the tangent line to the graph of f at the point C, Fc. And the quotient on the right hand side, Fb minus Fa over B minus A, give us the slope of the secant line, AB. I mean the straight line that go through A and B. And two straight lines have the same slope. It means that they are parallel. So here you see, we can find a number C. So that the tangent line to the graph of f at the point C axis is parallel to the secant line, AB. And if FB equal FB, the secant line AB is parallel to x-axis, and that's why we get right back the row theorem. Okay? It's very easy to memorize the theorems. Now, I go back to the row theorem. Yeah, it's here. Now, the function f is continuous on the closed interval AB, differentiable on the open interval AB, and Fa equal Fb. In this case, there is a number C between A and B, so thus f prime of C equals 0. F prime of C equals 0, it also means the number C is a root of the equation f prime of x equals 0. Now let me write out the equation for you here. Wait. F prime of C equals 0 means C is a root of the equation f prime of x equals 0, right? F prime of C equals 0 means C is a root of the equation f prime of x equals 0. Here C is in between A and B. So the conclusion of the row theorem can be restated as the equation f prime of x equals 0 had at least one root in the open interval AB. The equation f prime of x equals 0 has at least one root in the open interval AB. And that's why we can apply the row theorem to prove a given equation had a root in a given interval AB. So normally, to solve that a given equation, for example, the given equation given by, for example, g of x equals 0, and we want to solve that this equation had at least one root in the open interval AB. How to prove it? Normally, we consider a function, let's say capital G of x on the interval AB, the closed interval AB. And derivative of the function capital G with respect to x equal small g of x or any x of the open interval AB. Okay, and if the function capital G satisfy the condition, satisfy all conditions of the Rolle theorem, I mean capital G is continuous on the closed interval AB and capital G is differentiable on the open interval AB and GA is equal to GB, then that this a number C, so thus G phi of C equals 0. I mean capital G phi of C equals 0. Okay? Just a moment, please. So, if the function capital G satisfies all conditions of the Rolle theorem, then that is a number C. So thus, the derivative of the function capital G at C equals 0. It means C here is a root of the given equation. Right? Okay. Normally, we consider a function capital G. So that the derivative of capital G equal the function small g. Okay? And in mathematics, what does it mean? It means the function capital G here is called an antiderivative. An antiderivative of the function small g. What does it mean in Vietnamese? Antiderivative. It means in Vietnamese it means nguyên hạt, right? Okay. All right, now we consider some example. Wait. Okay. Now look at example 3.2b. We consider the quadratic equation ax squared plus bx plus c equals 0. Here a is a non-zero number. Now we assume that A, B, C satisfy the condition A over 2012 plus B over 2011 and plus C over 2010 equals 0. And now we want to show that the given quadratic equation had at least one root in the open interval 0, 1. All right. Actually, we can consider the general problem. Here, we can replace the number 2010 by a number m. M here is just a natural number. Okay, now let me show you the general problem. Let me share another slide here. Wait. Can you see the new slide? Mai Phương?
Yes.
Okay. Now here, suppose that A, B, C are real number and M here is a natural number. It means M may be equal 1, 2, 3, 4, 5, and so on. And in the previous example, M equal 2010. Okay, actually, we can give the solution for general case. Something like this. We suppose that A, B, C are real number and M here is a natural number. And suppose that A over M plus 2 and plus B over M plus 1 plus C over M equals 0. In this case, we can solve that the given equation, I mean ax squared plus bx plus c equals 0 had at least one row in the open interval 0, 1. Okay. In the previous example, M is just 2010. All right. And now, how to prove it? Normally, when we apply the row theorem, we consider a function capital G. So that derivative of the function capital G equal the left-hand side of the given equation. What does it mean? It means here, normally we think that maybe we consider the function G given by. We need a function G so that the derivative of the function G equal ax squared plus bx plus c, right? And that's why the function G should be like this. Ax cubed over 3. I try to write out something here. Okay, wait. Ax cubed over 3 plus b x squared over 2 and plus cx over 1, right? Normally, we consider the function G like this. Ax cubed over 3 plus bx squared over 2 and plus cx over 1. Okay. Why we consider this function? Because you have got here, if the function G, I suppose that the function G satisfy all conditions of the row theorem. And then the row theorem implies that there is a number C. So that g phi of C equals 0. Right? Okay. It means C is a root of the quadratic equation. Ax squared plus bx plus c equals 0. Because the derivative of the function G give you ax squared plus bx plus c, right? Okay. Now, all we have to do here is we check whether the function capital G given by ax cubed plus bx squared plus cx satisfy all conditions of the function, satisfy all conditions of the row theorem or not. Okay, the function G is a polynomial. Polynomials is a very nice function. It's continuous everywhere, differentiable everywhere. The key thing here is we check condition. We check the condition G of 0 equal G of 1 or not. If you have got this condition, then the function capital G satisfy all conditions of the row theorem. And then there is the number C between 0 and 1, so that g phi of C equals 0, right? Okay. So clearly, G of 0, to replace x with 0, you have got 0 plus 0 plus 0, it gives you 0, right? And G of 1 gives you a over 3. I try to write down something. Okay, wait. Plus b over 2 and plus c. right? But a over 3 plus b over 2 plus c may be different from 0. I mean, maybe g of 0 is different from g of 1. And that's why the condition g of 0 equals g of 1 does not satisfy. Huh? Okay? And that's why we have to improve the function capital G a little bit. Sometimes we have to improve the function G a little bit. And in this example, I consider the following function. You see, a x to the m plus 2 over m plus 2, and plus b over m plus 1 times x to the m of plus 1, and plus c over m times x to the m. Why? Why we consider this function? Now I explain. What is the function f? Clearly, f here is just a polynomial. Keep in mind that m here is a natural number. Okay? And by the way, the above function g, I mean ax cubed over 3 plus b x squared over 2 and plus c. Make the condition g of 0 equal g of 1. How? When m equal 1, right? Okay. So here we consider the general case. M may be number 2, number 3, number 4, and so on. Now we consider this function. F of x given by a over m plus 2 times x to the m plus 2, and plus b over m plus 1 times x to the m plus 1, and plus c over m times x to the m. Here we consider this function on the closed interval 0, 1. Clearly, the function f is continuous everywhere. That's why it's continuous on the closed interval 0, 1. The function f is differentiable everywhere because the function f is just a polynomial. So the function f is differentiable on the open interval 0, 1. Moreover, you have got here f of 0 equals 0. Clear, huh? If we replace f with 0, you have got f of 0 equals 0 plus 0 plus 0 and give you 0. All right? And f of 1 give you a over m plus 2 and plus b over 1 and plus c over m, and it's equal 0 by r. So the function f satisfies all conditions of the row theorem. And that's why there is a number x0 of the open interval 0, 1. So that's f prime of x0 equals 0. Okay, yeah. So f prime of x0 equals 0. What does it mean? You have got f of x. You can evaluate f prime of x easily. What is f prime of x? Derivative of x to the m plus 2 give you m plus 2 times x to the m plus 1. And that's why the derivative of the first term give you a x to the m plus 1. Derivative of x to the m plus 1 with respect to x give you m plus 1 times x to the m. And that's why the derivative of the second term give you b x to the m. Similarly, the derivative of the last term give you c x to the m minus 1. And that's why f prime of x0 give you something like this. Huh? A x0 to the m plus 1 plus b times x to 0 to the m and plus c pi x0 to the m minus 1. You can push x0 to the m minus 1 at a common factor, and you have got the following product. See? Because x0 is between 0 and 1, it means x0 is different from 0. And that's why it gives you ax0 plus ax0 square plus bx0, huh? Not square here. Okay, correct it yourself. Plus c equals 0. It means 0 is a root of the given quadratic equation. All clear, guys?
Yes, yes, I understand.
All clear, Quân?
Yes.
All right. So here you see, sometimes we have to improve the function g a little bit, huh? Here we call it the function f. Why we consider the function f given by a x to the m plus 2 over m plus 2 and so on. Actually, the function f comes from an antiderivative of ax squared plus bx plus c after we improve it a little bit. Any questions? All clear?
Thầy ơi. Alo.
Okay, go ahead.
Cho em hỏi chút xíu là thông thường á, khi mà mình làm cái dạng bài này á, thì mình sẽ dựa vô cái function mà thầy muốn chứng minh nó bằng không và thầy tìm cái antiderivative function của nó. Nhưng mà làm cách nào mà thầy ý là làm cách nào mà thầy đoán được nó là a ít mũ m cộng 2 chia cho m cộng 2 cộng chấm chấm á thầy. Ý là em vẫn đang hơi confused ở chỗ đó.
All right. Actually, I explained it already, but you don't understand it, right? Okay. Yes. Now, I go back. Okay, I go back. What we discussed here. All right. So, look, ax squared plus bx plus c equals 0. Okay. Yeah. And normally we think about find a function capital G, so that the derivative of the function capital G give us the left-hand side of the given equation. In our case here, it's just ax squared plus bx plus c. So, what is an antiderivative of the function ax squared plus bx plus c? I mean, we find the function capital G, so that derivative of capital G give you ax squared plus bx plus c. Exactly, here you have got ax cubed over 3 plus bx squared over 2 and plus cx, right? Okay. And if we consider the function g given by ax cubed over 3 plus bx squared over 2 plus cx, okay, the function g is continuous everywhere, differentiable everywhere. The key thing here is whether the function g satisfies the condition g of 0 equals g of 1 or not. Keep in mind that here we want to show that this a number, that this a root of the given equation in the open interval 0, 1. And that's why we consider the function capital G on the closed interval 0, 1. So the key thing here is whether the function capital G satisfy the condition g of 0 equals g of 1 or not. So clearly g of 0 gives you 0, right? You replace x with 0. A times 0 cubed over 3 gives you 0, right?
Yes.
Okay. And now, what is g of 1? When you replace G of 1, I write out it already in the chat box. You see here, A over 3 plus B over 2 plus C. Whether we have got A over 3 plus B over 2 plus C equals 0?
We're not sure.
It holds only when M equals 1, right? Here we assume that's A over M plus 2 plus B over M plus 1 plus C over M equals 0. Here M is a natural number. And M is an arbitrary natural number. M maybe equal 1, maybe equal 2, maybe equal 100. It's okay. Any natural number, okay? For any natural number, we can solve up the quadratic equation ax squared plus bx plus c equals 0. So the function ax cubed over 3 plus bx squared over 2 plus cx allow us to prove that ax squared plus bx plus c equals 0 had at least one root in the open interval 0, 1. If we have got a over 3 plus b over 2 plus c over 1, okay, equals 0. It means it gives us just it gives us a solution just for a particular case when m equals 1. Right? Okay. It gives us just a particular solution of the given equation. It also means we just prove it for m equals 1 only. And that's why here we have to improve the function g a little bit. I mean, we improve the function ax cubed over 3 plus bx squared over 2 plus cx a little bit. And we try to consider a function so that we can use the condition a over m plus 2 and plus b over m plus 1 and plus c over m equals 0. It's so that thus we consider the function f of x given by a over m plus 2 times x to the m plus 2 plus b over m plus 1 times x to the m plus 1 and plus c over m times x to the x. Here x belongs to 0, 1.
Okay, I understand now. Thank you, teacher.
All right. Now we turn to the second example. Wait. All right, now look at example 3.2a. Now, we want to solve that the equation x cubed minus 3x plus alpha equals 0 cannot have different root in the closed interval 0, 1 for any value of alpha. What does it mean? It means that the given equation cannot have two different roots. Cannot have two different roots. What does it mean? It means the given equation cannot have two roots, x1, x2. x1, x2 here belong to the closed interval 0, 1. How to prove it? Actually, it follows directly from the row theorem. And the proof is very, very easy, very, very elementary. My Phương, and then you have got a solution. Maybe you make this problem already in high school. Phương?
Yes.
Yeah, okay. And could you tell me your solution?
We apply the Rolle theorem, right?
Yeah.
So
you met this problem already before?
it may be the same, but
Okay. Yeah.
use different technique.
All right. Yeah. Okay, let me show everybody in the class my solution. And you see, it's a very, very simple. It's really a simple solution. Now, let me share another slide. Yeah, it's clear here. Can you see my slide?
Yes.
Can you see the slide, guys? So we want to solve that the equation x cubed minus 3x plus alpha equals 0 cannot have different roots in the closed interval 0, 1 for any real number alpha. Here, we apply proof by contradiction. Okay? You learn proof by contradiction from the beginning, right? Okay. Now, we assume that exactly here, a sum on the contrary thus. A sum on the contrary thus. In Vietnamese, something like giả sử ngược lại rằng. Okay? Here, I just write a sum thus x cubed minus 3x plus alpha equals 0 had at least two different rows in the closed interval 0, 1. Let's say x1 and x2. I mean, we assume that the given equation has two rows x1, x2. Here, x1, x2 is between 0 and 1, and x1 less than x2. Okay? Now, if we consider the function x cubed minus 3x plus alpha on the closed interval x1, x2. Once again, the function f is just a polynomial of order 3. It's continuous everywhere. It's differentiable everywhere. And moreover, you have got f of x1 equal f of x2 equals 0. Right? Because x1 is a solution. Actually, here the function f given by the left-hand side of the given equation. Here, you see, I just take the left-hand side of the given equation. You see? And you have got f of x1 equal f of x2 equals 0. It also means all conditions of the Rolle theorem are satisfied. I mean the function f satisfies all conditions of the Rolle theorem. So there is a number c. So that's f prime of c. Okay, I missed prime here, right? Okay, f prime of c equals 0. There is a number c between x1, x2. So that's f prime of c. I missed prime here, huh? Wait a moment, please. All right, I get back right now. Okay. So, by the Rolle theorem, there exists a number C between x1 and x2. So thus f phi of C equals 0. I made phi here, okay? Correct it yourself. What does it mean? It means the equation f phi of x equals 0 had at least one root between 0 and 1. Exactly here, C greater than 0, less than 1. However, now, if we consider the equation f phi of x equals 0, you will see here, f phi of x gives you 3x squared minus 3, right? And f phi of x equals 0 gives you just two roots, 1 and minus 1, right? It is impossible. This is a contradiction. By the Rolle theorem, that is a number C between 0 and 1, so thus f phi of C equals 0. However, it is impossible because f phi of x gives you just two roots, 1 and minus 1. And that's why our assumption from the beginning, I mean, x cubed minus 3x plus alpha equals 0 had two different roots in the closed interval 0, 1 is wrong. A proof by contradiction. Okay. Here, I think it's better if we remove this paragraph before we apply the Rolle theorem. It's better. We remove it and put it here. Okay. Maybe it's better. All clear, guys?
Yes.
Other student? Trúc Linh, you understand it, Linh?
Yes, teacher.
Okay. V, Bảo Vi.
Yes, teacher.
Okay. Okay. Hoài Thu.
Yes, teacher.
You got it? You understand it or not?
Yes, I understand.
Okay. Okay. Good. Okay. Yeah. So correct it here. F phi, huh? Not F. Yeah. I forgot phi here. Okay. Yeah. All right. Now we go back the Rolle theorem, mean value theorem, and so on. Now let me go back the slide. Okay, it's here, huh? Okay, can you see the new slide, Phong?
Yes, yes.
Okay, now look at the corollary 3.3. It says that if f phi of x equals 0 for all x in an interval I, then f must be a constant function on this interval. Okay, you learned it in high school already. Okay. The question here is how to prove it. How to prove it? Actually, it follows directly. It follows directly from the mean value theorem. The proof is very, very simple. Now let me show you. Okay, can you see the new slide?
Yes.
Okay, now I assume that f phi of x equals 0 for any x of the open interval AB. And then f must be a constant function on this interval. How to prove it? What is a constant function? Normally, maybe you think that a constant function is mean f of x equal x. F of x equal 1 for any x, or f of x equal 2 for any x, and so on. Okay? Yeah, it's right. And the general definition here means a function f is a constant function if the value of f of x does not change when x varies on the interval AB. What does it mean? It means for any x1, x2 of the open interval AB, f of x1 equal f of x2. The value of f of x does not change when x varies on the open interval AB. It means for any x1, x2. x1, x2 are fixed but arbitrary. At what I wrote here, you see, let x1, x2 belong to the open interval AB, be fixed but arbitrary. Cố định nhưng mà bất kỳ. Alright, okay. And we can assume that x1 less than x2. Now, we show that f of x1 equal f of x2. Here, x1, x2 are arbitrary number of the open interval AB. We just apply the mean value theorem. Okay, yeah. Here we apply the mean value theorem on the closed interval x1, x2. You have got f of x2 minus f of x1 over x2 minus x1 equal f prime of c. Here, c is a point in the open interval x1, x2. I mean that this is a number c. C is between x1, x2. So that's f prime of c equal f of x2 minus f of x1 over x2 minus x1. We just apply the mean value theorem to the function f on the closed interval f1, f2. Okay. However, we have got f prime of x equals 0 for any x of the open interval AB. That's why f prime of c equals 0. Because c here is just a point, it's just a number of the open interval x1, x2. Of course, the interval x1, x2 is just a sub-interval of the open interval AB. That's why you have got c here belong to AB. It gives you f of x1 equal f of x2, right? It means f is a constant function. It follows directly from the row theorem, the mean value theorem, okay? And by the way, you learned in high school already. Okay, let me remind you. If f prime of x positive for any x of the open interval AB, then f is increasing on the interval AB. And if f prime of x negative for any x of the open interval AB, then f is decreasing on the open interval AB. How to prove that? It follows directly from the mean value theorem. Now, for example, we prove A. We suppose that f prime of x positive for any x of the open interval AB. Then we show that f is increasing on the open interval AB. Now we assume that x1 less than x2 and x1, x2 belong to the open interval AB. It means you have got x1 greater than A, x2 greater than x1, and B greater than x2, right? Okay. Now we apply the mean value theorem to the function f on the interval x1, x2. We get the same as the above, huh? Okay. So that this number c between x1, x2. So that's f prime of c equal f of x2 minus x1 over x2 minus x1. And this time, f prime of x positive for any x of the open interval AB. And that's why here, f prime of c positive. Because c here belong to AB. And that's why the quotient f of x2 minus f of x1 over x2 minus x1 must be positive, right? Moreover, you have got x2 minus x1 positive already. And that's why f of x2 minus f of x1 must be positive. Because x2 minus x1 positive already. x2 greater than x1. It means you have got f of x2 greater than f of x1. So here, if x1 less than x2, then f of x1 less than f of x2. So the function f is increasing. You see here the fruit follow directly from the mean value theorem. Okay? Yeah. You learned them in high school already. Now you should learn how to prove it. Actually, it follows directly from the mean value theorem. Okay? All right, I give you some example. Here, a very, very familiar example. Now, okay, can you see the new slide? Quân. Tấn hả? Tấn ngọc Quân. I don't remember. Quân, right? Okay, Quân. Are you there, Quân?
Yes.
Okay. Can you see the slide?
Yes.
Okay. In high school, you use very, very often sine of x squared plus cosine of x squared equal 1 for every x, right? I do believe that everybody, every student in this class learn it already and use it very, very often in high school. You use it very, very often in high school, right? Okay. The question here is how to prove it. Actually, we can prove it easily. Yeah. So here, sine of x squared plus cosine of x squared equal 1 for every x. What does it mean? It means the function on the left-hand side, sine of x squared plus cosine of x squared, is just a constant function because it's equal 1 for every x. So first, it must be a constant function. And that's why here I consider the function f given by sine of x squared plus cosine of x squared. We consider this function on the interval minus infinity, infinity. Okay? Now, first, we show that f must be a constant function. How to show that f must be a constant function? We show that derivative of the function f equals 0 for every x of the interval minus infinity, infinity. It's easy, right? By a very simple computation. By a very simple computation, you have got f prime of x equals 0, right? We apply the chain rule here. Derivative of sine of x squared give you 2 sine of x, and derivative of sine of x give you cosine of x. Similarly, derivative of cosine of x squared give you 2 cosine of x times derivative of cosine of x give you minus sine of x. So clearly it give you 0, right? Because f prime of x equals 0 for every x, so f must be a constant function. I mean f of x equal a for any x. A here is a constant. So what is the number a here? F of x equal a for every x, and particularly we have got f of 0 equal a. On the other hand, when you replace x with 0, you have got sine of 0 square plus cosine of 0 square and give you 1, right? Sine of 0 give you 0, cosine of 0 give you 1. And that's why you have got f of x equal 1 for every x. This means you have got sine of x squared plus cosine of x squared equal 1. for every x. All right, one more example. One more example. Can you see the new example, Phong?
Yes, teacher.
Okay, now we want to show that 2 tan inverse of x. I mean 2 arctangs of x. Or we can say 2 tan inverse of x plus sine inverse of 2x over 1 plus x squared equal pi for every x greater than or equal to 1. All right, how to prove it? So, if we consider the function f given by the left-hand side, I mean f of x given by twice tan inverse of x plus sine inverse of 2x over 1 plus x squared on the interval 1 infinity. Then you have got f of x equal pi for every x greater than or equal to 1, right? So first, it means that the function f must be a constant function. And that's why now, first we show that f is a constant function. How? We just show that derivative of the function f equals 0 for any x of the open interval 1 infinity. Just open interval 1 infinity. It's step 1. Okay? All right. Now, derivative of tan inverse of x gives you 1 over 1 plus x squared. That's why you get the first term, 2 over 1 plus x squared. Now, how to get the derivative of sine inverse of 2x over 1 plus x squared? Of course, we apply the chain rule, right? Apply the chain rule, we get something like this now. 1 over square root of 1 minus 2x over 1 plus x squared all squared. And tie the derivative of the quotient 2x over 1 plus x squared. Tie the derivative of this quotient. We apply the chain rule, nothing else. Huh? Okay. By a very simple computation, we simplify something. Okay. You see here, derivative of x over 1 plus x squared gives you 1 minus x squared over 1 plus x squared and all square. We apply the quotient rule here. And as you can see here, it gives you 0. So the function f must be a constant function on the closed interval 1 infinity. A here is a constant. F of x equal A. Now we determine the constant A. As in the previous example, to find the number A, we should choose a special number, let's say x0 of the closed interval 1 infinity, so that you can evaluate the value of f at that point easily. In the previous example, we consider we choose x0 is just 0, right? Okay. Here I choose x0 here just 1. Why? Because here when f equals 1, I can evaluate f of 1 easily. Just twice tan inverse of 1 and plus sine inverse. Correct it. Sine inverse of 2 over 1 plus 1 is mean 1, huh? So it gives you 2 times pi over 4 and plus pi over 2, it gives you pi. What we expected, huh? Sine inverse, correct it. I just write something like ARC. Sine inverse, correct it here like this. Now let me write down. Sorry. Like this, All clear, guys?
Yes, yes.
So here, actually, this problem reduced to problem, just evaluating derivative of the given function. Just the function given by the left-hand side of the given equation, right? This problem actually just the problem evaluating derivative of the function f given by the left-hand side of the given equation. You see? All clear? Okay, I go back to the main slide. Wait. All right, can you see the new slide?
Yes, I see it.
Okay. So this theorem is very, very familiar to you. It's called the first derivative test. So suppose that C here is critical point of a continuous function f, and if f prime derivative of f change from positive to negative at C, then f has a local maximum at C. And if f prime change from negative to positive at C, then f has a local minimum at C. And if f prime do not change sign at C, f has no extremum at C. It's a very, very familiar to you. You learn it in high school, and you did it many, many times in high school, right? Okay, it's so clear. I want to discuss this theorem. This is called the second derivative test. Now, look, suppose that f double prime is continuous near C. What does it mean? It means we assume that the function f has second order derivative in a neighborhood of C. I mean f double prime of x at this for any x in some interval C minus delta, C plus delta. Near C is mean f double prime of x is continuous on the interval C minus delta, C plus delta, a neighborhood of C. Okay, and then if f prime of C equals 0, what does it mean? It means C is critical number. Moreover, f double prime of C positive, then f had a local minimum of C. And if you have got f double prime of C negative, then f had a local maximum at C. How to prove it? Actually, it's a very elementary. Now let me give you the proof. I say another slide. Wait. Yeah, it's here. Can you see the slide, Phong?
Yes.
Other student, can you see it now?
Yes.
Yes.
Yes, yes.
Okay. First of all, let me remind you the second derivative text. Okay, I just restate what we discussed about. So suppose that f double prime is continuous on the interval AB.
Yes.
And C here belong to AB. Any questions? Okay, so here, suppose that f double prime is continuous on open interval AB, and C here belong to AB. It means AB here stand for a neighborhood of C. Huh? Okay, maybe you can replace the interval AB by the interval C minus delta, C plus delta for some positive number delta. And now, if f prime of C equals 0 and f double prime of C positive, then f has a local minimum at C. Why? And how to prove it? All right. Similarly here, if f prime of C equals 0 and now f double prime of C negative, then f has a local maximum at C. Here the proof. Now we prove A only. Okay. Now we have got f double prime is continuous on the interval AB, and C belong to AB, and that's why f double prime of x is continuous at C. I mean, the function f double prime is continuous at C. Okay, and that's why we have the limit of f double prime of x at x approach C equal f double prime of C. I just apply the definition of limit. I just apply the definition of continuous function at a point. Okay, yeah. The function f double prime continuous at C. So you have got the limit of f double prime of x at x approach C equal f double prime of C. So you see here, the limit of f double prime of x at x approach C positive, and that's why we can find a number delta. So that's f double prime of x positive for all x in this interval. I mean C minus delta, C plus delta. We just apply the definition of epsilon delta. Okay? You remember we have got the following result. We discussed already in the previous chapter. Okay. You remember if you have got, let me write down something here. Huh? The limit of f of x. Okay, I say g of x. Huh? Change notation. At approach C, greater than number A. Okay, and then we can find a neighborhood of C. I mean, we can find a number delta so that g of x greater than A for any x of the interval C minus delta and C plus delta. So if the limit of g of x at x approach c at this and greater than a, then we can find a neighborhood of c. I mean, we can find a number delta. So that g of x greater than a for any x of the interval c minus delta, c plus delta. Here a is just number 0, right? Okay. Now, look. You have got the limit of f double phi of x at x approach c greater than 0. And that's why we have got f double phi of x greater than 0 for any x of the interval c minus delta, c plus delta. Okay? F double phi of x greater than 0 for any x of the interval c minus delta, c plus delta. So it implies that f prime is increasing on this interval. It's clear, huh? And now, in high school, we often create the following table. In high school, we often create this table, right? Now, we just pay our attention to the function f, f prime, and f double prime on the interval c minus delta, c plus delta only. Okay. First of all, you have got here f double prime of x on way positive. Okay, I write out here. Double, not prime, huh? Here f double prime. Okay. So you have got plus here. F double prime of c positive 2, huh? Okay. And you have got f prime of c equals 0 by our assumption here. F prime of c equals 0. So you have got 0 here. And keep in mind that f prime is increasing. And that's why you have got f prime is positive on the interval c plus delta. Because f prime is increasing. And f prime of c equals 0. And similarly, f prime of x negative on the interval c minus delta. Because the function f prime is increasing. So you see here, f prime change sign at c. It changed from negative to positive. And that's why f of c gives you a local minimum. All clear, guys? All clear? Mr. Kwon, you understand it, Kwon?
Yes.
Khánh Minh, you understand the fragment? Thảo Nguyên. You hear me, Nguyên? You understand it or not?
Understand.
Okay. Read it yourself again at home. All right. Okay. So here, you see the fruit is quite simple. Huh? Here we apply a very basic properties of limit of a function at a point. F double prime of c positive and f double prime of x is continuous at c, and that's why we can find a neighborhood of c. So that's f double prime of x positive on this interval, on this neighborhood of c. And you can drive that, f prime of x change sign at c. It change from negative to positive. And that's why f of c gives you a local minimum. By the same way, you can show that if f double prime of C negative, then f of C give you a local maximum. Okay? Ngọc Yến, you understand the proof, Yến?
Yes, teacher.
Okay, good. Okay. Anyway, everybody read it again at home. Okay? Yeah. All right, we consider one more example. Before we have got a break. Huh? Now let me see. Yeah, maybe we consider this example. Can you see example 3.5?
Yes.
Okay, look. Question A, so that the function f of x given by x plus e to the x is increasing on the interval minus infinity, infinity. It's easy, right? How to prove it? We just show that f prime of x positive for all x of the interval minus infinity, infinity, right? Clearly, f prime of x give you 1 plus e to the x. It's always positive, right? So question A is so easy. Just show that f prime of x is positive for any x. Now, question B, we want to evaluate derivative of f inverse at 1. Now you see here, from question A, the function f is increasing. Exactly, it's strictly increasing. I mean, if x2 greater than x1, then f of x2 greater than f of x1. The function f is strictly increasing. And that's why f is one-to-one function. F is one-to-one function, so f inverse at this. Okay, and now we want to find the derivative of f inverse at 1. Okay, you remember you learned a formula for derivative of f inverse already. Now let me remind you here. Here you see, we already know derivative of f inverse of 1 equal 1 over f prime of f inverse of 1. Actually, here in general, we have derivative of f inverse at x equal 1 over f prime of f inverse of x. Okay? So, the first thing here is we have to determine f inverse of 1. What is f inverse of 1? F inverse of 1 here. Now, we have to determine f inverse of 1. Now, let me write down here for you. F inverse of 1. So, what is f inverse of 1? We suppose that f inverse of 1 equal A. F inverse of 1 equal A, it means that f of A equal 1 by definition of inverse function. Okay? And what is f of x? F of x given by x plus e to the x, and that's why f of A give you A and plus e to the A, right? Okay, That's why we have to determine the number A. So that's A plus e to the A equal 1. So what is the number A? We want to find a number A. So that's A plus e to the A equal 1. What is the number A? Aha. Kimchi, what is the number A? Chi? Thảo Nguyên, what is the number A? You hear me? Chi? All right. What is the number A?
Zero.
A equals 0, right? Here you see. We have to determine a number A. So that's A plus e to the A equal 1. It means f of A equal 1. And clearly 0 is a solution. If you replace A with 0, you have got 0 plus e to 0, it gives you 1. Right? And keep in mind that f here is a one-to-one function. So 0 is a unique number. So that's f of 0 equal 1. And that's why here, derivative of f inverse of 1 equal 1 over f prime of 0 only. You see? And all we have to do here is we evaluate f prime of 0. Okay, f prime of f give you, let me see, clearly f prime of f give you 1 plus e to the x. So f prime of 0 give you 1 plus 1 give you number 2. So you get 1 over 2 here. Okay? 0 is a unique number. So that's f of 0 equal 1. Because here, the function f is increasing. F is one-to-one function. Moreover, f is increasing. You see? All clear, guys? Hello? All clear?
Yes, yes, teacher.
Okay, have practice. Now, let me see. We get back at, okay. 255, okay? Yeah. I write out here. Ủa, có mấy bạn không nghe được hả? Yến đâu rồi? Yến? Lê Ngọc Yến.
Em đây thầy.
Là sao? Thấy ghi
Dạ
là thầy
mấy bạn kim chi bị lag á thầy, nên là bạn không có trả lời được nên em nhắn giùm á thầy.
Okay. Sometimes we get a problem because here we are now in online class now. Okay, have practice. All right, get back the class play. Can you hear me?
Yes.
All right. So now I want to discuss some optimization problem. What does it mean? We discuss some application of derivative of function of one variable to some real world problem. Okay? So you have got a model, and in the model, we have to find the maximum value, minimum value of a function. Now we get started with the following problem. Can you see the new slide?
Yes.
Nó hơi nhỏ thầy. Yes.
All right. Let me enlarge a little bit here. Let me see. It's quite small, right? All right, how about now? It's better?
Yes.
Okay. Now look at the first example. An open rectangular box with square base. We have got a rectangular box, and an open rectangular box means we have got no top. We have got 4 sides and a base. So an open rectangular box with square base is to be made from 48 square feet of material. What dimension will result in a box with the largest possible volume? So roughly speaking, you have got 48 square feet of material, and you want to make an open rectangular box with the maximum volume. So you have to determine dimension of the box so that you have got a box with maximum volume. All right. Now, how to answer the given questions? What dimension will result in a box with the largest possible volume? Now we introduce two variables. Let x be the length of one edge of the square base. Keep in mind that the base is just a square, and now we call x is just the length of the square base, and y here is just the height of the box. Okay, we have got 4 sides, right? And the area of one side is just x multiplied y. One side, a side gives you just a rectangle. And the area of the base gives you just x times x, it means x squared. And that's why you have got the total area of the box equal x squared plus 4xy, and it's covered by 48 square feet, right? Now, what is the volume of the box? Clearly, the volume of the box gives you just x squared multiplied y. The height by the area of the base, right? Here. The volume of the box given by x squared multiplied y. So we have to find the maximum volumes of V. V here is a function of two variables, x and y. V here given by x square multiplied y. And we have got a constraint here. By a constraint, I mean a condition. X square plus 4xy equal 48. Okay. So roughly speaking, we have to find the maximum value of the function v. V here is a function of two variables x and y, and it's given by x square multiplied y. And xy satisfy the condition x square plus 4xy equal 48. Here v is a function of two variables x and y. All right. If you learn analysis 2 already, for example, Miss Fung, okay, you understand that we can find the maximum value of v as a function of two variables. Here in analysis 1, you learn how to find the maximum value, minimum value of a function of one variable only. And that's why we have to reduce the function v into function of one variable. And from the equation x squared plus 4xy equal 48, you have got y equal 48 minus x squared over 4x. And that's why v now becomes just x squared times 48 minus x squared over 4x. And now we just find the maximum value of the function v as a function of x, a function of one variable only. If you learn linear algebra, if you learn analysis 2, you know how to find the maximum value of function of two or more variables. Here we reduce this problem into finding the maximum value of function of one variable only. Find the maximum value of function of one variable. So v of x here given by 48x minus x cubed over 4. Here x is a positive number. Okay, how to find the maximum value of v? You learned it already. We find critical number, right? And we consider sign of derivative as critical number. And we can conclude something. Yeah? Here. We find critical number. We just saw the equation v phi of x equals 0. Okay, v phi of x equals 0. Keep in mind that x here must be positive. So you have got only one critical number, number 4. Moreover, clearly, v phi of x change from positive to negative when x go through 4. I mean here, v phi of x positive when x less than 4, and v phi of x negative when x greater than 4. It means v phi change from positive to negative when x go through number 4. So v4 gives you the maximum value of v. It means the function v attains a maximum value at number 4, and v4 equal 32. X equal 4, you have got y equal 2. And you get the dimension of the box with the largest volume. So the key thing here is we create the function v. It gives you the volume of the box. And using the condition x squared plus 4xy equal 48, we reduce v to a function of one variable. Here v is a function of x only. And then we can show that v attain the maximum value at number 4. More precisely here, v phi change from positive to negative when x go through 4. And that's why v4 gives you the maximum value of v on the interval 0 infinity. Okay, one more example. Huh? All clear, guys? Any questions? All clear?
No question, teacher.
Okay, one more example. Now, one more example. Look. A movie screen on a wall is 20 feet high and 10 feet above the floor. At what distance X from the front of the wall should you position yourself so that the viewing angle theta of the movie screen is as large as possible? So look at the figure, you see? We have got a movie screen. It is 20 feet high and it is put 10 feet above the floor. Okay, it's so clear, huh? Look at the figure, you see? Now we want to determine our position so that we get the best view. This means we get the maximum value for theta. Yeah, as you can see here, huh? So, as in the previous example, first we try to represent theta as a function of x. Here, x is the distance from our position to the wall. Here, we introduce a variable. X is the distance from our position to the wall. As you can see here, huh? Now, the first step here is we try to represent theta as a function of x. And then we find the maximum value of theta. Of course, here x should be positive. Now, how to represent theta as a function of x? Yeah, you see here. How to represent theta as a function of x? Okay. Now, as you can see here, we introduce a new angle alpha. All right. So clearly, tan alpha give you just tan over x. It's clear, huh? Tan alpha give you tan over x. And that's why alpha here is just tan inverse of tan over x. Similarly, tan of theta plus alpha equal 30, right? 20 plus 10 give you 30 over x. And that's why theta plus alpha is just tan inverse of 30 over x. So theta here is just tan inverse of 30 over x minus alpha. It means theta here is given by tan inverse of 30 over x minus tan inverse of 10 over x. So we finish the first step, and the key step, we represent theta as a function of x. The next step, we just find the maximum value of theta as a function of x on the interval 0 infinity. The key thing here is we can represent theta as a function of x. Now, how to find the maximum value of theta as a function of x? As usual, we find critical number of theta, and then we consider sine of derivative of theta at critical number. Yeah, you see here. We find critical number of theta. So we evaluate theta phi of x. And we solve the equation theta phi of x equals 0. Keep in mind that here x is a positive number. So it gives you just 10 square root of 3. Moreover, you can check theta phi change from positive to negative, huh? Here, theta phi of x positive when x less than 10 square root of 3, and theta phi of x negative when x greater than 10 square root of 3. So the function theta attains the maximum value at 10 square root of 3. And the value of theta at 10 square root of 3 give you pi over 6. The best view to enjoy the movie. All clear, guys? All clear?
Yes, teacher.
All right. One more example. Yeah, you see here. Look. Can you see the new example, guys? Can you see the new example? Can you see the new example?
Yes, yes.
Okay. So here you have got a semicircle of radius 3. Just a semicircle. Now we want to determine the dimension of the rectangle of largest area. Thus can be inscribed in the semicircle. So here you see, we introduce two variables, h and w. And clearly the areas of the rectangle is just w times h, right? And the key thing here is we try to find a relation between w and h. And as you can see here, we have got h squared over w over 2 square equal 9. It's so clear, huh? It's so easy to see this equation, to see this relation between h and w by the Pythagorean theorem. X squared plus w over 2 square give you 3 square. It's so clear, huh? So clear. All right, so the area of rectangle give you x times w. Now we reduce a to a function of one variable. From the relation between h and w, you have got w is just 2 square root of 9 minus h squared. We can solve this equation for w. Keep in mind that w and h are positive number. And that's why a now is a function of h, and a given by 2h times square root of 9 minus h squared. Of course, here h is between 0 and 3 only. Of course, h is between 0 and 3. I mean h greater than 0 and less than 3. So, mathematically, we have to find the maximum value of the function a on the interval 0, 3. Now we find critical number. We solve the equation. Derivative of a with respect to x equals 0. You see. And it gives you just square root of 3. We have got just one critical number. And moreover, we can solve that. Okay, we can solve that. Here, the function a attain the maximum value as square root of 3. Check it yourself, huh? Okay, here you have got, let me see, derivative of a with respect to x give you, You have got 2 times 9 minus h square and minus 2 square. And that's why here you have got 18 minus 4 h square. Okay, it's so easy. 8 change from positive to negative when 8 go through square root of 3. It's a very easy, very similar to the above example. Check it yourself. Okay, read it yourself home. Now I give you time to practice now. Let me see here. All right. Now I give you time to practice. Do it now. Play. Read it yourself and show me your solution. Do it now. Play. I give you 15 minutes. Do it now. Play. Isosceles triangle has height A scales of length 3 and BC of length 2 and a point P is placed along the line segment A scale. What is the minimum of the sum of the distance from P to AP to B and from P to C? So what does it mean? It means we want to find the minimum of the sum PA plus PB plus PC. Okay, I give you 15 minutes. Do it now and show me your solution. Okay, 15 minutes. All right. Have you got a solution? Any solution? Okay, okay. Now look, let me help you a little bit here. Okay, so let me help you a little bit. To solve this problem, we have to introduce a variable. Okay, a variable. Now here, the question here is a find the minimum of the sum of PA plus PB plus PC. Okay. So here, for example, we introduce new variable x equal PA. Okay. And then we can evaluate PB, PC in terms of x. I mean, you can represent PB, PC in terms of x. Okay, it also means PB, PC is a function of x. So what is PB? Clearly, you see PB equal PC, right? Because here you have got isosceles triangle, tam giác cân. All right. P here lie on the straight line AQ, and Q is the middle point of BC. All right, you see here. AQ gives you the height of the triangle. AQ gives you the height of triangle. So you have got here PB equal PC, PB equal PC. And clearly you have got PB equal PC equal, let me see, equal square root of PQ square and plus no, PQ square plus QC square, QC square. Pythagorean theorem. PB equal PC equals square root of PQ square plus QC square. And you have got AQ equal 3. You have got AQ equal 3 already, okay? AQ, the height of the triangle, and the length of HQ equal 3. PA is equal x, so PQ, you just 3 minus x. PQ give you 3 minus x. BC equal 2, so QC give you just 1, just a half, just a half, right? And that's why here you have got PB equal PC equal, let me see, square root of, let me see, okay. Here just 3 minus x square, and plus 1, right? PB equal PC is equal square root of 3 minus x square plus 1 square. And that's why here PA plus PB plus PC give you just x plus 2 pi pb. It means twice square root of 3 minus x squared plus 1/2. Here, x is a positive number. So here, PA plus PB plus PC give you a function of x. Exactly here you have got x plus 2 square root of 3 minus x squared plus 1. Here x is a positive number. Now you just find the minimum values of PA plus PB plus PC as a function of x. When you have got x, I mean when you have got the point x0 at which PA plus PB plus PC get the minimum value, you have got the position of P on the straight line AB. Okay? So, complete the solution by yourself at home. Okay? I got some solution here. Now, let me check. Yeah, your solution is correct form, of course. Huh? Another way, here's a, maybe we call P skills is just X. We introduce another variable. X here is just PQ. It's okay, no problem. Now let me see my firm. Yeah, the same, huh? It's correct, Phương? All right. All right. Now, maybe the last example for today. Can you see the new slide, Phùng?
Dạ thấy thầy.
Okay. So, rate it yourself and show me your solution. Okay, I give you 15 minutes. Do it now before I show you my solution. Okay, everybody do it yourself. I give you 15 minutes. Do it now, please.
Thầy ơi thầy.
Any questions?
Cái đề nó hỏi cái gì á thầy? Em đọc không hiểu lắm.
Kiện thôi để nói tiếng Việt cho mọi người hiểu cái đã nha. Phương, can you understand it, Phương? Mai Phương?
Dạ, con hiểu là tìm cái đường ống, ý là đặt cái đường ống làm sao cho nó, ý là cái đường ngắn nhất để tới cái điểm
không phải đường ngắn nhất. Tức là ok, mình có một cái giàn khoan dầu ngoài biển á, đúng không? Thấy ngoài này không? Thì người ta cho cái khoảng cách từ cái giàn biển này đến cái bờ biển rồi, tức là cái khoảng cách D này bằng 10 miles, được chưa? Ok, rồi người ta cho cái khoảng cách mà từ cái hình chiếu của cái giàn khoan ngoài biển á, thấy chưa? Hình chiếu của nó trên cái bờ á, đến cái nhà máy lọc dầu này á, là khoảng cách là N là 20 mile, đúng chưa? Bây giờ người ta phải đặt một cái đường ống dẫn dầu từ cái giàn khoan phía ngoài khơi á, đến cái nhà máy để mà lọc dầu chứ, đúng không? Thế thì cái giá của cái ống mà đặt ở dưới nước á, nó khác cái giá mà đặt ở trên khô. Đây nè, nó cost 25 million per mile của cái ống mà dưới nước. Cái đường ống mà dưới nước á, thì nó cost, cái giá của nó là 25 triệu trên một mile. Còn cái giá mà đặt trên khô á, trên bờ á, thì nó ít hơn, nó chỉ 10 mile thôi, nó chỉ 10 million trên mile thôi. Thấy chưa? Vậy thì bây giờ mình đặt cái ống làm sao mà để cái cost là nhỏ nhất, tức là mình tiêu phí nhỏ nhất. Có nghĩa là mình tìm cái điểm trên bờ này. Ví dụ như mình đặt x là khoảng cách đây, khoảng cách từ cái thằng hình chiếu của cái giàn khoan lên cái bờ đến cái vị trí mà mình cần đặt ống dưới nước cho đến khi nó tiếp xúc với bờ. Thấy chưa? Thấy cái x không? Đó, thì mình gọi x là cái khoảng cách đó. Thế thì cái thằng S mình tính được, đúng không? Thằng S chính là cái gì? Thằng S á, chính là cái khoảng cách của cái đường ống nằm dưới nước. Phải vậy không? Còn cái đoạn ống mà đặt ở trên khô, trên bờ chẳng qua chính là L trừ X thôi. Và như vậy mình lấy cái S này nè, mình nhân cho 25 cộng cho L trừ X nhân cho 10. thì ra cái chi phí, ra cái cost của đặt đường ống. Và mình phải tìm cái minimum của cái hàm đó. Hiểu không?
Dạ hiểu rồi thầy.
Đây earns oil rigs is 10 miles out the sea and the refinery that the oils need to go is 20 miles up the shoreline from the oil rig. Okay. See the figure. It costs, if it costs $25 million per mile to place a pipeline in the water and $10 million per mile on land. Where should the pipeline make landfall in order to minimize cost? Tức là mình tìm cái điểm ở trên bờ mà sao cho là khi mà mình được đặt cái đoạn đường ống dưới nước và đặt cái đoạn đường ống mà trên bờ á, thì chỉ là cái tiêu phí, cho mình cái tiêu phí nhỏ nhất. Vậy thôi. Okay, just write out the function for which you have to find the minimum value. Okay, just write down the function for which we have to find the minimum value. Do it now, please. Hello, can you hear me?
Yes.
The rain coming is very heavy, so maybe you cannot hear anything, huh? It's very noisy. All right, I give you the function f. So find the minimum value of f. Okay. Maybe we stop here. See you next week, huh? I close the class session right now.